So molecular shape and molecular polarity are related to each other. We've talked about polar bonds. This is HCl, and the chlorine has a higher electronegativity, is more attractive to the electrons than the hydrogen, and so there's a dipole moment, which we can represent as an arrow pointing to the more electronegative one with a plus here on the plus side. And I think of that as like Dad is out in the driveway and somebody comes over, where's the kids? And he points at the house that's got the more attractive stuff, right? So this is Dad pointing. Another way to do that is with the lowercase Greek delta. So it's a change, a difference, but it's small. So this is negative and positive. Low electron density over here, high electron density over there. If you have a diatomic molecule with just two atoms, if the bond is polar, the molecule's polar. If the bond is nonpolar, the molecule's nonpolar. But when you have more than two atoms, the geometry gets involved because those dipole moments can cancel each other out. So if we look at carbon dioxide, carbon dioxide has two double bonds. These are both polar bonds. The oxygen's more electronegative, and so the electrons are being pulled out towards the oxygen. And on the other side, this oxygen is also more electronegative than the carbon, and so this is pulling the electrons out in this direction. So you could think of this a little bit as like playing tug of war. So this is the rope here, and this carbon is like the flag in the middle, and here you've got one person over here tugging on the rope, and one person over here tugging on the rope. These oxygens are the same element, they have the same electronegativity, they are equally strong. So when two equally strong people pull against each other, does the flag on the rope move? No, nothing happens. It's just kind of stuck there, right? So the electrons are not going to get shifted to one end or the other of the molecule. And so even though this has two polar bonds in it, the molecule is nonpolar. It doesn't have a positive and a negative end. And what we're really doing here is we are adding vectors in three-dimensional space, which if you liked that in whatever math class they teach that in, you'll be like, oh, okay. And if you didn't like that, I'm not going to torture you with it. But these vectors, these dipole moments, they have a direction and they have a magnitude. So the direction we get by looking at the electron geometry of the molecule, and then the strength would be related to the electronegativity difference between those two atoms. And we're not going to get into picky details about that. So if we look at water, water has a bent shape because of its two lone pairs. The lone pairs have an impact on the molecular geometry, but once we set that molecular geometry, we don't have to consider them for polarity of the molecule. So this oxygen-hydrogen bond is polar. Oxygen's more electronegative. Oxygen's pulling this way. And here, that same oxygen is pulling that way. So here, the hydrogens are not opposing oxygen straight across. They're at an angle. And so oxygen can pull the whole business, right? So if we think about it, if oxygen's pulling against these guys, he can pull this way and it will move. That's going to pull the electron density over to this end of the molecule. So the oxygen end will be a little bit negative and the hydrogen end will be a little bit positive. So that's a polar molecule. let's see. I'll jump ahead to my shortcut. This works almost all the time. It's not perfect, but it works a lot, and it's so much easier than thinking about adding vectors. So a molecule will be nonpolar if both of these things are true. There are no lone pairs on the central atom, and all the atoms bonded to the central atom are the same or have the same electronegativity. So we'll go back and answer some of these questions now. So molecular shape and polarity, you start with the Lewis structure and look at electron groups and electron geometry and get the molecular geometry. And then you're looking to see, well, are there any polar bonds? So if it's two different nonmetals other than carbon and hydrogen, you should assume it is a polar bond. And if you're going to add vectors, then you have to identify which direction is it pointing to. It's pointing to the more electronegative, and then you've got to figure out how to add those vectors. So a molecule contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? Well, it can be helpful to draw a picture. So it's a trigonal planar. And these are polar bonds. So, we could draw the vectors here. If that has a trigonal planar molecular geometry, does this central atom have a lone pair? Could it? No, it can't. So there's no lone pairs here. And these atoms have the same electronegativity because those bonds are identical. So another way to think of this is, here's this poor guy in the middle, and you've got 3 people pulling on him in opposite directions. Now, he's going to be hurting tomorrow after getting pulled all over the place like that. But would this group of things move? No, because you have opposing forces. So tug of war works in 2 dimensions. 3 dimensions gets a little uglier. But the shortcut is, are there any lone pairs? No. Are all of these the same? Yes. Both things are true. It's nonpolar. Is the molecule polar? No. So this goes over vector addition. If you like that, you can read it and you'll understand it and it'll be good enough. There's my shortcut. Oops. So let's determine if CF4 is polar. We have to start with the Lewis structure. So carbon and 4 fluorines around it. And then just to be complete, we'll put in all the lone pairs. So we could do the whole thing with all the, the vectors and stuff. Let's use my shortcut. Are there any lone pairs on the central atom? No. Are the atoms bonded to the central atom the same? Yes. So this is nonpolar. So why does this shortcut work? Nonpolar molecules are symmetrical. If they have polar bonds, the bonds oppose each other in exactly opposite directions, and so they add up to 0. So when you don't have any lone pairs in there, it's going to be a symmetrical geometry. If you have a lone pair in there, that's going to push the atoms and the bonds over to one side. It's automatically going to be lopsided. what if, instead of fluorine here, what if this was iodine? Now it's going to be polar, because iodine does not have the same electronegativity as the fluorines. This guy is weaker pulling on the electrons. It's not symmetrical anymore, and so then that would be polar. So the polarity of molecules is important because it is very predictive of some of their properties. So here we have a container with oil, could be vegetable oil, and water, like Italian salad dressing without the flavorful stuff, right? So if you put a lid on this and shake it up, you can get it to kind of mix together, right? But as soon as you set it down, the oil's going to float up to the top, and the water's going to go to the bottom, and you're going to have these two separated layers. The reason it does this is because water is polar and oil is nonpolar. Polar molecules, because they have these partial charges, will be attracted to each other like weak magnets. They're not like ions, not as much as an ion, but they have weak charges. So the hydrogen end of water is attracted to the oxygen end of another water molecule. So like magnetic marbles, they're going to stick together. Oil is nonpolar. It's just carbons and hydrogens. All of its bonds are nonpolar. Doesn't matter what shape it is if all the bonds are nonpolar. So those would be like regular glass marbles. And you can imagine what would happen if you dumped a bunch of marbles together. Some are magnetic and some are not. The magnetic marbles are going to clump together, and they're going to exclude the non-magnetic ones. So what happens here with oil and water is the water molecules are really attracted to each other. They're not attracted to the oil molecules. The oil molecules aren't very attracted to each other either. And so water is like a really big clique of mean girls, right? They're just like so into themselves, and they're going to exclude anybody else that wants to come in. The reason the oil is on the top is because it's less dense. You can also have situations like this where the nonpolar thing is more dense than water, and then that layer will be at the bottom. Any questions?
That pretty much explain like metal conductors with electricity?
No, this is not related to metal conductors. It does explain how soap works. I changed the inner tube on my bike today and got my hands just filthy. It's like water is not going to fix this problem, right? I need soap, right? You know, you get butter on your hands or Crisco or bacon grease or something. You can rinse your hands all you want. It's not coming off, is it? You got grease from the car. It won't come off. You need soap. Well, why does soap work? Well, this is an example of a soap molecule. So we've got this long tail that's all carbons and hydrogens. This is all nonpolar bonds. This part is very nonpolar. At one end of this molecule are some oxygens. This is a polar head on this soap molecule. So this end of the soap molecule can interact with the water molecules. And this nonpolar end can interact with the grease and the oil. And so what happens is, you know, here you've got your glob of grease, right? So you're going to have the polar heads of the soap molecules around the outside, and their tails, their nonpolar tails, are going to be in the grease or oil. So the tails get in with the grease. It's going to break the grease into little tiny pieces called micelles. And they're going to be coated on the outside with these polar heads that interact really well with water. They speak Mean Girl, right? So they can go through this click and not, get booted out. And so this will break up the grease into little tiny pieces that can float around in the water and they'll wash away. Any questions?